All right, let's take a look at our Incline Lab data. First, let's take a look at our image. So this is what's going on. We had our car, which was going down the ramp, and what we have is the weight going down, the normal force, which is perpendicular to the plane, the friction force, which is going opposing motion going up the plane, and the kinetic or action force going down the plane. This is what we're going to work with mathematically, but remember from today's discussion that there's only 3 real forces working on this. So on the AP exam, this force body diagram would be a dot for the car, weight going straight down, the normal force perpendicular to the plane, and then friction going straight up. As you can see here, there's no kinetic force because the kinetic force actually comes as a component of weight. So it would not be drawn on a force body diagram. When we take a look at this, we sum the forces in X and we sum the forces in Y. So sum the forces in Y is pretty simple. Because the car isn't going through the plane, we know it's going to equal 0. So F sub Y is equal to F sub N plus the Y component of the weight, which is mg cosine theta. That's this right here. And it's negative because it's going in the opposite direction. We're saying up is positive, so therefore down is negative. And this then sums to 0. Now in the X direction, it doesn't equal 0, and this is because it speeds up as it goes down the plane. So some of the forces in the X direction are, and we're going to say down the plane is positive and up the plane is negative. So F sub K plus F sub F is equal mass times acceleration in the X direction, which is not equal to 0. Do some substitutions. F sub K is equal to, or F sub K plus mu Fn, which is our F sub F is equal to mu Fn, which is equal to mu mg cosine theta. And F sub K is equal to the X component of weight, so it's mg sine theta. So we put this all into our equation. Mg sine theta minus mu mg cosine theta is equal to mass times acceleration. Since we have mass on both sides, we can cross it out. So we can see that it is mass independent. So then we are left with g times sine theta minus mu cosine theta is equal to the acceleration. And if we wanted to solve for mu, then we just do a little bit of algebra. So sine theta minus ax over g times 1 over cosine. And that would give us our mu. This is what it looks like in terms of drawing it out. Now let's take a look at the data. In class, you measured a few things. The whole number, and remember, we're measuring the whole from the physics base up. Theta, what I've done here is you can see is that theta is actually done in the real numbers. So in your original lab, you probably have different numbers, and that's okay. Gravity, wing length in meters, and then TA, TB, and TAB. All of these you measured. Then we did some calculations. The calculations for A measured comes from the last lab. So that was wing length times TA minus TB all over TA, TB, TA times TAB. And we can see this here in our formula. Getting to understand how spreadsheets work can be really powerful. We have over 113 data points in this set, and doing each of these calculations by hand would have been rather horrific. Now, this was equal to g sine theta, which is not having anything to do with friction yet. So that's why we can see our percent difference is so bad here. So since the A down the plane is g sine theta, we had to use theta. But in spreadsheet programs, they like it converted into radians. So we use the function radians, and then we take the sine, and then we multiply it by gravity. And the nice thing is once you do it once, then you can copy and paste the formula into every other box. So all I did was create these formulas one time, and then I copied them and pasted them into the rest of the cells. So you're not retyping every time. That's the power of Excel. Now, percent difference is just equal to the real minus the experiment over the real, and then I took the percentage. So you can see without the accounting of friction, we've got really, really bad data here. 70% off, 50% off, 40% off. It got a little bit better here as we get higher and higher angles. Frictions seem to have less and less of an influence. So 20, 21, so the best we seem to have done was low teens in terms of our percent error. So we know that g sine theta isn't a good model for our force of action going down the plane. We need to incorporate friction. With this, we then need to know the mass of the car plus one plate. So the mass of the car plus one plate was something that I measured in lab. So that is just, I used two scales because our scales don't go up high enough. So put it across two scales, added one plate weight, divide by 1,000 because our scales measure in grams and we do all of these calculations in kilograms. I had to make sure that it was in kilograms. So this would be a source of error easily if you weren't being careful. So then I broke it down into the components, and F sub W, which would have been down the plane, is just equal to g sine theta. And so that's equal to E is equal to mass times gravity, and so that's the weight. And then the components of this, again in radians, is equal to, we need to find out the d, which is our theta, convert it into radians and take the sign, and that's multiplied by our weight. So that's the component in the x direction for weight. And then we did the same thing in the y direction. And I made it negative here because it's in the opposite direction of our normal force, which is in the positive direction. So the force of weight in the y direction, negative, and again, just the only difference was the change in our trig function, so that's cosine instead of sine. Normal force was just equal to mass times gravity times the cosine of theta, and so we can see here that it's equal magnitude, opposite in direction, as it should be because the car did not sink into our plane. Now we start to play, and this is the real power of using a spreadsheet versus using your calculator. Is because I know the friction force has to be equal to mu, and I can choose any mu I want, times F sub n. So I have the normal force, and again I did negative because I wanted this to come out to be friction force being negative because my action force was positive. So all this is our R3, which is the nice thing is if you don't like something, you can undo it. So this is equal to our normal force times 0.1. Again, when mu is closer to 0, it means it's more slippery. As mu approaches 1, it gets more and more sticky. I chose mu's that were in increments of 1/10. And so I've got a friction force here for 0.01 up to 0.09. And so these increments are going to then help us in our next part. So please watch the second video to see where we go from here.